Hello, I'm Sebastian. Welcome to 9R Trees podcast. Today, I will summarize and review the book. Deep Learning, Foundations and Concepts by Christopher M. Bishop presents a rigorous, concept-first pathway into modern deep learning, guided by the perspective of a leading researcher and educator. Rather than treating neural networks as a collection of recipes, the book emphasizes why common architectures and training methods work, grounding them in probability, optimization, and representation learning. Readers can expect careful development of essential ideas such as function approximation, gradient-based learning, regularization, and the role of inductive bias, along with an informed view of how deep models connect to broader machine learning principles. Bishop also frames deep learning as part of a larger scientific toolkit, linking neural methods to classical statistical modeling and highlighting where deep learning excels and where it can fail. The overall tone is analytical and unifying, aiming to build durable intuition that transfers across tasks like vision, language, and structured prediction, and across model families from multi-layer perceptrons to contemporary architectures used in practice. I will give you key takeaways from this book. Firstly, deep learning as a principles-driven extension of machine learning. A central theme is that deep learning is best understood through enduring foundations rather than fast-changing tricks. The book situates neural networks within the broader landscape of statistical learning, showing how model design and training choices reflect assumptions about data. Concepts like generalization, inductive bias, and capacity help explain why deep models can perform well despite being highly flexible. By connecting neural networks to probabilistic modeling, the reader can interpret outputs as predictions with uncertainty-related considerations and understand losses as measuring mismatch between model and data-generating processes. This perspective also clarifies tradeoffs between expressiveness and robustness. Deeper or wider models can fit complex patterns, yet need structure and constraints to avoid brittle behavior. The discussion highlights how representations emerge across layers, enabling reuse of features and compositional reasoning, which is a key advantage over shallow approaches. Importantly, the principles-driven framing helps readers evaluate new architectures critically. Instead of adopting methods because they are popular, readers learn to ask what problem structure a method exploits, what assumptions it embeds, and how those assumptions affect performance across domains and shifts in data. Secondly, optimization and training dynamics in deep networks. Training is presented as an optimization problem shaped by non-convex landscapes, gradient-based methods, and numerical stability. The book emphasizes the logic of backpropagation as efficient differentiation of composite functions, making clear how gradients flow through layered structures. From there, it builds an understanding of why variants of stochastic gradient descent are effective in practice. Mini-batches provide noisy but informative gradient estimates that can scale to large datasets and can sometimes help escape poor regions of the landscape. Readers are guided to think about learning rate selection, momentum, and adaptive methods as tools that interact with curvature, scale, and noise. Training dynamics also depend on initialization, normalization, and architectural choices that influence gradient propagation and signal scaling. The practical implications are substantial. Stable training reduces time to convergence and improves final generalization. The book also helps readers reason about debugging. When loss plateaus, diverges, or overfits, the underlying cause often lies in optimization settings, data preprocessing, or mismatched objectives. By framing optimization as a systematic component of model design, the reader gains a transferable mental model for training both classical deep networks and newer architectures. Thirdly, regularization, generalization, and controlling complexity. Deep models can memorize, yet they often generalize impressively when trained with the right constraints. The book explores this apparent paradox through multiple lenses that illuminate how effective complexity is controlled. Regularization is not only a penalty term in the loss, it also arises from architectural priors, data augmentation, early stopping, noise injection, and parameter sharing. Weight decay can be understood as a preference for smoother functions, while dropout and related techniques encourage redundancy and reduce co-adaptation among units. Data augmentation embeds invariances, effectively enlarging the dataset with transformations that preserve labels, which is especially powerful in perception tasks. The narrative connects these methods to the bias-variance trade-off and to probabilistic interpretations that treat regularization as encoding prior beliefs about parameters or functions. Beyond technique, the book encourages readers to think in terms of failure modes: overfitting due to spurious correlations, underfitting due to insufficient capacity or poor features, and poor generalization under distribution shift. By learning how regularization mechanisms interact with optimization and representation learning, readers can make principled choices that improve reliability and reduce the need for brute force hyperparameter tuning. Fourthly, architectures and representation learning for structured data. A major contribution of deep learning is the ability to learn representations that align with structure in real-world data. The book explains how architectural design encodes inductive biases that reduce the burden on data and training. Convolutional networks exploit locality and translation-related structure through shared filters and pooling, making them efficient and effective for images and other grid-like signals. Sequence models and attention-based approaches address variable length inputs and long-range dependencies in language, audio, and time series, using mechanisms that control how information is aggregated. The key concept is compositionality. Layers build higher-level features from simpler ones, enabling abstraction and reuse. The book also discusses how such architectures trade flexibility for stability, often improving sample efficiency and generalization. Another emphasis is the relationship between architecture and objective. Choices like output parameterization, loss functions, and decoding strategies determine what the model actually learns, particularly in classification, regression, and structured prediction. By learning to map problem structure to architectural bias, readers gain a practical framework for selecting models that are not just powerful, but well matched to the task and constraints. Lastly, probabilistic viewpoints, uncertainty, and modern deep learning practice. Bishop is known for connecting machine learning to probability, and this book reinforces the value of probabilistic thinking in deep learning. A probabilistic viewpoint helps interpret predictions, compare models, and reason about uncertainty, which is critical in high-stakes settings. The book highlights how common losses relate to likelihood-based training and how outputs can be calibrated or miscalibrated depending on data, model, and training procedure. It also encourages readers to distinguish between different kinds of uncertainty, such as ambiguity in the data versus uncertainty about parameters, and to consider what information a model should convey beyond a single-point estimate. This framing supports better decision-making in deployment, thresholds, abstention, monitoring, and evaluation. Under shift, all benefit from uncertainty awareness. The discussion complements practical deep learning workflows, including dataset design, validation protocols, and the importance of reproducibility. By integrating probabilistic principles with contemporary deep learning concepts, the book offers a coherent language for understanding why methods work, how to compare alternatives fairly, and how to build systems that behave predictably when conditions change. In conclusion, this book is best suited to readers who want a durable understanding of deep learning rather than a quick tour of tools. Graduate students, researchers entering the field, and engineers who already use neural networks but want stronger theoretical grounding will benefit most. It is also valuable for experienced practitioners who need to justify modeling choices, communicate assumptions, and diagnose training or generalization problems systematically. The main life benefit is confidence and clarity. By learning to connect architectures, objectives, optimization, and regularization under a unified set of principles, readers can design models more efficiently, reduce trial and error, and make better judgments about reliability and risk. That translates into better outcomes in real projects, where data is messy, constraints are real, and deployment requires more than leaderboard scores. Compared with many deep learning books that emphasize code or rapidly changing best practices, Bishop offers an integrated conceptual map that remains relevant as specific architectures evolve. The focus on foundations, probabilistic interpretation, and careful reasoning makes it a worthwhile purchase for anyone building long-term expertise, because it strengthens intuition that transfers across tasks, domains, and the next wave of methods. If you would like to support Christopher M. Bishop, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.